Hello there, welcome to my question of the day. This is number 13 in a series I've been running every day on my Facebook page. This is taken from a maths challenge paper. It's an intermediate level 1 and it's to be done without a calculator. I don't know why that's working like that. Right on there. No calculator. So if you've just found this problem, please feel free to have a go and press pause while you're doing it, and then I'm going to go through it. It's a bit of a long one today, I'm afraid. Okay, so the diagram shows a hexagon and all the interior angles of my hexagon are 120 degrees. And I'm focusing on that piece of information for the moment because I think that's going to be quite important. When I'm looking at this diagram, I'm just going to quickly draw red angles that are all 120 degrees. Well, that implies that every single exterior angle is going to be 60 degrees. I can draw an exterior angle there. I can draw an exterior angle here. Oh, hang on a minute. The final angle in that triangle I've just drawn must be 60 degrees. I must have an equilateral triangle there. How exciting. Okay, if I look on the bottom right-hand corner, I can make another exterior angle, which is 60 degrees inside there. And I can make another exterior angle. Oh my goodness, so exciting. I have yet another equilateral triangle this time. The sides are the same but different from the ones at the top. In the top equilateral triangle, and lo and behold, if I draw exterior angles, I can see the bottom left hand side is also an equilateral triangle. That is so exciting because that is what's going to unlock this problem for me. By doing that, I can see that I have a much bigger equilateral triangle because all of its interior angles are 60 degrees. I know that because in each 3 corners I have the same angle, so therefore the sides must all be equal as well. Well, that tells me that the lengths of that big equilateral triangle are 11 units long. So I've got a little plan, and my plan is that in order to find the area of the hexagon, I think what I'm going to do is going to find the area of the big triangle, and I'm going to subtract the area of the 3 other triangles inside it. So that's kind of my plan. I like making a plan of action. So it's not going to be easy, and I think I'm going to need something else to help me. I have a big diagram down here which I'm now going to get rid of because I think I'm actually going to need quite a little bit of space here in order to do my workings out. Right, so let's look at the biggest triangle that I have in my diagram. And the biggest triangle I've got is 11, 11 and 11. And in order to find its area, I really need to do its base, multiply by its height and divide that by 2. The only problem is I need its vertical height, and its vertical height, its perpendicular height, I don't have, but I do notice that it's going to split the base in half. I can see a right angled triangle inside there. So if I look at 1/2 of that triangle, because it has a line of symmetry being an equilateral triangle, so I know therefore that it must be divided into 2 congruent triangles that are both right angled. Now Pythagoras' theorem is going to be really important here. If I have the 2 short sides of a right angled triangle, I call them A and B, and the longest side I call C. And I know that A squared plus B squared is going to equal C squared. And it's actually the height B. In fact, I'm going to change that B to an H. It doesn't really matter what symbol it is, but the relationship between those 3 variables has to be the same. Now, in order to find that height, what I'm going to have to do, height squared is C squared minus A squared, just rearranging there, and the height therefore must be the square root of C squared minus A squared. So I'm going to be using that as I'm working as well. Right, so going on to this triangle then. where the base is now 11 over 2 and the length there is 11, and I'm going to call this h. So to find h squared, first of all, I'm going to do 11 squared minus 11 over 2 squared. Okay, that's fine. I'm just going to tidy that up a little bit. I'm going to get the denominators to be the same. So I'm going to have 4 lots of 121 over 4 minus 121 over 4, which leaves us with 3 lots of 121 over 4. Now to find the height, I'm going to have to square root that whole fraction. Let's have the 121 first. Nice, I can see some square numbers in there. Now there's a little property with surds, if you didn't know already, that I can square root the numerator of a fraction, I can square root the denominator of a fraction. And then if I'm multiplying roots together, I can split them up like that. So I can see that the height is going to be, well, the square root of 121 is 11, can't root 3, so I'm just going to leave it like that, and root 4 is 2. So I have an expression for the height of that triangle. Now, remembering that it's that big equilateral triangle that I want to find the area of, and I've got the base times by its height, all divided by 2, or I can multiply by a half, it has the same effect. I'm going to get 121 root 3 over 4. That is going to be very useful. So that's that biggest triangle there. Okay, so I'm going to label that as the area of my big triangle. Right then, so have a look at the diagram. Now, if I have a look at the top triangle next, so I'm going to start colour coding this, otherwise I'm going to get into all kinds of trouble. I'm not quite sure what colour to make it, because they're all, I don't think they're going to go really well with my pen at all. However, that is pink now, so you're just going to have to deal with that. So I have a length down here of 2, a length up there of 3. The whole length in that green long length is 11, so 3 and 2 is 5, so take that away, 6 there. Right, so the top equilateral triangle has lengths of 6. Okay, so the top triangle looks like this. Colour it in pink so you know where it came from. And it's got a height as well, of course. Right, we've got to find that first. So that's 3, that's 6, and that's my height. So I'm going to go through this process every time. Now the height has to be the square root of 27. Now I notice that a square number that divides into 27 is 9. 9 times 3 is 27. That means I can break that down into root 9 times root 3, and the height is 3 root 3. Lovely. So therefore, the area of my pink triangle now is going to be the base, which is 6 times by the height, 3 root 3, all divided by 2. That's 18 root 3s divided by 2, which leaves me with 9 root 3s. Nice. That's the area of my pink triangle. Good. Let's go back up to the question again. Right, so I need a different colour this time. I'm going to have a luminous blue. Oh, yes, excellent. That is a triangle, equilateral with lengths of 2 units. Okay, cool. So we've got the bottom right triangle. Which is blue. 2, 2, 2, looks like that. Height, just redrawing, so 1, 2, and my height is there. Height squared is 2 squared minus 1 squared, that's nice, which is 3, so my height is root 3. The area of my blue triangle, remember, is going to be the base times by the height, and then divided by 2, and that is root 3 units squared. That was nice and easy. And then I'm going to have a look at the bottom left triangle. My writing's deteriorating as I'm going through this video, but maybe that's no bad thing. Okay, right, the triangle on the bottom left has lengths of 1. So it looks like this, 1, 1, 1. colour it in so you know where it's from. And there's my height. And that must be 1/2. So height squared is 1 squared minus 1/2 squared. Be careful when I'm squaring fractions there. Height squared is 3/4. Okay, that means the height is the square root of 3/4, which is √3/2, because I'm square rooting the 3, square rooting the 4. If you're fluent with square numbers, it really, really helps. Right, now the area of my yellow triangle is base times height divided by 2, or multiplied by 1/2, it's probably easier here, and √3/4. Okay, so I have all of the areas that I need. Okay, so as mentioned before, now I think I'm going to get a navy pen now, and I'm going to make it slightly thicker. So the area of the 3 small triangles, might be easier to just add them up, is 9√3, add √3, add √3/4. So I have got 10√3s, add √3/4. I would really like denominators to be the same there. So I'll have 40√3/4 and √3/4, which means that they add up to have 41√3/4. Okay, remembering that the area of my big triangle was 121√3/4. So now I'm going to find the area of hexagon. And I'm going to get the biggest area, take away the areas of the little triangles that have been cut out. That's going to leave me with 80√3/4. 80 divided by 4 is 20. 20√3 units squared. Looking back to the answers, I really hope 20√3 is there. And if I have a look at the answers, A is the one. Now, I am not saying that my way is the best. It's just the way I did it. It's the way I saw the problem initially. I thought that I wouldn't need a calculator. There are lots of other ways. You could have used trigonometry to find the area of a triangle. Without a calculator, for some people, they would really struggle with that. And I know that this question is aimed at pupils in year 9, 10 and 11. Some really good year 11 pupils might be able to cope with trigonometry without a calculator, but they would be in the minority. So I think that the method I've used is probably more accessible for people who are doing a GCSE in maths. And if I was doing an A-level in maths, I'd probably refer to some non-right-angled trigonometry in order to do that. Anyway, I hope you haven't fallen asleep, or maybe you might be listening to this video to cure your insomnia. Either way, I hope you've enjoyed it on some level. If you want to leave any comments below this video, I'll be very glad to read them. If you want to make your way over to my Facebook page, I'd be really happy for you to do that. You can follow the problems each day. And if you want to find out more details about my tutoring service, please drop me a message. Thanks very much. Goodbye.